Okay, hello everybody. My name is Baptiste Saleil. I'm a PhD student at Université de Montréal in Canada, supervised by Marc Feeley. And today I will present you some results of my my current research. So my research currently focuses on the implementation of dynamic languages and especially how we can solve the problems introduced by dynamic languages using lazy dynamic techniques instead of using expensive static analysis. So for my PhD, during my PhD, I built a compiler called LC that is a JIT compiler for Scheme, and the compiler is described in two papers published in the Scheme and Functional Programming workshop. And actually, the technique I will present you today is implemented in our compiler, but you can easily implement it in any other dynamic languages. So it's pretty cool because we just had a great introduction on dynamic languages. So we know that if you want to implement dynamic languages, we have less work done at compilation and we increase the work done at execution. So if we take, for example, dynamic type checking, the compiler does not check the type at compilation, but inserts the type checks in generated machine code to ensure the safety of the primitives. So that's pretty cool, but because the runtime are executed, the checks are executed at runtime, it negatively impacts the performance. So we can take this simple code as an example. Here we have a pretty simple function that takes an argument x and add the number from x to 10 by adding 1 at each step. So if you want to compile this code, we have to insert exactly 4 type checks. So we have, because we don't know the type of the argument, we have to insert 3 checks on x for the greater operator and the both additions. And we have to add another check to check the type of the value returned by the Redshift call. So we say that it has a negative impact on the performance. So the challenge is to remove these checks, but we still want to ensure the safety of the primitive. So actually, there are several ways to remove this type checks. For example, we can use static analysis, but I will talk about static analysis in a minute. And another solution is to use code specialization. So we can just take again this example with 2 calls to the sum_to_10 function. And in this example, it's actually pretty easy for the compiler to determine that the 2 calls to the sum_to_10 function actually refer to the function that it's just defined above, because we only use a first-class function here. So if we use a JIT compiler to execute this code, when the execution reaches the first call to the sum_to_10 function, here the compiler knows the identity of the call function. It also knows the type of the argument, because here we have a constant. So it can just generate a specialized version of the sum_to_10 function, specialized using the information that the argument is an integer. Then when the execution reaches the second call to the sum_to_10 function, this time again the compiler knows the identity of the call function, and it also knows the type of the argument, so this time it can generate a specialized version of the function using the information that the argument is a floating point number. So this was pretty easy, so let's just complicate a little bit our example using higher order function. So here we have basically the same example, but instead of having a single summer, here we create a generator of summer. So the generator is waiting for the upper bound of the summer, and this bound is captured in the function f, and this summer is returned. Then we create 2 summer, a sum_to_10 function and a sum_to_p function with 10 and p, of course. And after that, we have 3 calls to these 2 summers. So we see that in this example, it's really less obvious that the 3 calls to the sum_to_10 to the sum_to_10 and sum_to_p function actually refer to the f function that's defined inside the make summer function. So once again, to find this information, we can use static analysis, for example, the well-known zero CFA analysis. But we have 2 problems with this kind of analysis. The first one is that they have high complexity, so it's not really JIT compatible. And the second problem is that they are imprecise in some case, meaning that we can't always determine the exact set of functions that are called at a given call site. So for this reason, we decided not to use this analysis. So to summarize, what we want to do is that we want to add the possibility to the compiler to do interprocedural specialization of code. We want this technique to be able to work in the presence of higher order function. We want the technique to work with dynamic languages. And finally, we don't want to use any static analysis. So this is a lot of things to do, but the good news here is that there is an existing technique called basic block versioning that do a good part of the work. Actually, this technique was introduced 2 years ago at ECOOP, and basic block versioning allows the compiler to do intra-procedural specialization of the code. It works with dynamic languages, and it does not require the use of any static analysis, so it's pretty good for us. So I take, again, our example. So here again, if we compile this code with a really naive compiler, this time we'll have to insert exactly 5 checks. So we have the 4 checks, like the same example before. And this time we have another check because we also want to check the type of the upper bound, so the captured value. When using basic block versioning, we will see that we can remove some checks. So because basic block versioning is a JIT compilation technique, the function is initially represented with a stub, and no code is generated until the function is called for the first time. So when we reach the first call to the sum210 function, when we call sum210 with the argument 6, the function stub, the compilation stub is triggered, and the compiler begins to compile the first basic block. So in this case, the first basic block is the condition of the if, so we want to generate the code for the greater operator, but before generating this code, we have to check the type of the x variable. So this is exactly what we do here. We generate a test to check if maybe x is an integer, and we create 2 new compilation stubs to handle the 2 outcomes of the check. And we can see that both compilation stubs are associated to an augmented context using the result of the previous check. So in this case, because we call the function with an integer, the true branch is executed and the stub is triggered, but this time we have the information that x is an integer, so we'll specialize the code using this information. Using the exact same mechanism, we'll continue to compile lazily the function and to propagate the information we discovered by specializing the code until we reach the end of the execution, and we can see that we have with basic block versioning, we have only 3 checks inserted in the code, and we remove 2 checks. So the reason why these 2 checks are removed, we can see, is because we actually discovered the type of x for the greater operator, and as I said before, the type is propagated, so it's not necessary to check the type of x again. But if we look closer at our example here, we see that each time we call the sum210 and sum2p functions, actually we know the type of the arguments. So if we add to the compiler the ability to propagate this information to the function call, we can actually also remove the first type check on x. Actually, exactly on the same way, if we add the compiler the ability to propagate the type to the function return, we can also remove the check needed to check the value, the type of the return value. And finally, there is only one remaining check, but we said before that the compiler is now able to propagate the type to the function call. So when we call the makeSummer function, we actually know the type of the variables. So if we propagate this type, the type of the captured variable is known when creating the closure associated to the function. This means that if we add the ability to the compiler to specialize the code using the capture information, all the checks are eliminated in this example. So a consequence of this is that now a function possibly has several entry points. Each entry point is specialized for a particular type combination, meaning that we have exactly 3 things to do. The first one is that we have to extend the closure representation to allow the compiler to store several entry points instead of 1. The second thing we have to do is to execute a dynamic dispatch at call site to branch to the corresponding entry point. And the last thing we have to do is to, like I said just before, we need to add the ability to specialize the code using captured information. So I will now explain how we implemented these 3 points in our compiler. So this is the flat closure representation that the compiler generally uses to represent the function. A flat closure contains exactly 2 things. The first thing is an address to the code of the function, and the second thing is a list of the value of the captured variables. So these figures shows how flat closure representation can be used to represent the 2 summer we create in our example. So on the top of the figure, you have the code generated by the compiler. On the bottom of the figure, you have the space where the stubs are located, and on the middle, you have just the two closures. So here we can see that the 2 closures contains only 1 capture variables. That is our upper bound. So we have 10 and p. So when the execution reaches the first call to the sum210 function, the compilation stub is called, the compiler is called, and the function is generated, and the address of the function is written into the closure. When we reach the second call to the sum210 function, this time the function already exists, so the control flows directly to the function. And when we reach the call to the sum2p function, because also the function already exists, we just patch the closure of the sum2p function. We can see here that the problem is that this closure representation allows to store a single entry point, and there is no way to store several entry points. So to solve this problem, we decided to introduce what we call an entry point table. Instead of writing directly the address of the entry point into the closure, we write the address of a table, and this table contains several entry points. And exactly like before, this table is initially filled with the stub address. This means that this time, when the execution reaches the first call to the sum210 function, we'll just use the first available slot in the entry point table. We'll associate the type combination of the argument. So in this case, we have just an integer. We'll generate a specialized version of the function, and we will write the address into the entry point table. So in the same way, for the second call to the sum210 function, there is no version yet generated for this context, so we generate a new version of the function. We write the address into the entry point table, and the version is executed. When we call the sum2p function, this time the version already exists, so the control directly flows to this version. There is one major problem here. The problem is that we said before that when we are compiling a call site, we do not necessarily know the identity of the callee function. This means that when compiling the call site, we don't know which slot is in the entry point table is associated to the current type combination. Sorry. So this is exactly why we need to execute a dynamic type check at call site to branch to the corresponding entry point. So to solve this problem, we decided to, well, actually there are several ways to implement the dynamic dispatch. You can actually perform a dispatch at call site, but we decided to base our implementation on position invariance for performance reason. So to do that, we introduce what we call the global layout. Actually, a global layout is just an association between an index and a combination of type. But the difference here is that all the entry point tables created for the program will follow this exact same layout. That's why it's called a global layout. So this time, if we represent all the closure created for this program, we first have a closure for the makesummer function with no captured variables. We have an entry point table for this function, initially filled with the stub. Then we have a call to the makesummer function. And this call triggers the step that triggers the compiler. So a version of the makesummer function is created, and a new closure is created for sum210 with a new entry point table. Actually, the interesting thing here is that the compiler associates in the global layout the first index to the type combination integer. So when we have the second call to the make summer function, this time we'll ask the global layout, so do we have an associated index for this type combination? Actually, there is no this type combination in the global layout, so we'll use the next available slots, and we'll add this association into the global layout. When we reach the first call to the sum to 10 function, we'll ask the global layout, and because this type combination exists, we will use this exact same index to generate a version of the f function. The exact same thing appears when we reach the second call to the sum to 10 function, and we generate a new version of the f function, and we patch the second slot of the entry point table. And for the last call, because the version already exists, the control flow directly to the version. Sorry, I come back. There is one remaining problem here. The problem is that we can see that the sum to 10 function captures a variable that is an integer, and the sum to p function captures a variable that is a floating point number, meaning that if they share the same table, we actually can't specialize the code using this information. So to solve this problem, we decided to specialize the entry point table. So instead of sharing the table by all the closure, the instance of the same function, we actually specialize the table each time we observe a different combination of capture variable types. So again, if we run our program with this extension, this time when we create the entry point table for the sum to 10 function, we had the information that the capture variable was an integer. Then for the sum to p function, this time we will not use the same entry point table, but we will use a new entry point table that is specialized for this new type combination. So nothing really changed for the two first calls, but when we reach the last call to the sum to p function, this time we'll generate a new version of the f function that is specialized using this information. So the interesting thing here is that we can specialize the code using both the type combination of the arguments and the type combination of the capture variables. Okay, that's pretty cool because it solved the problem for the function calls, but what about continuations? Actually, we know that continuation can be represented as call to the continuation. So conceptually, we can use the exact same implementation, but this time the propagated types is the type of the return value instead of the type of the arguments, and the captured type are the types of the local variables lived when we create the object representing the continuation for the call. So I have 2 minutes left to present you my results. So for our experiments, we use 35 benchmarks that are pretty standard benchmark used by major implementation, and we use 4 configurations for the compiler. But for this talk, I will talk only about the 2 main configurations. So intra-procedural only basic block versioning, and basic block versioning using our interprocedural extensions. So if we look at the number of executed type checks, actually this graph shows the number of executed type checks relative to intra-procedural basic block versioning, meaning that 100% is intra-procedural basic block versioning. And what we see in this figure is that for 9 of the benchmark, we completely remove all the dynamic type checks, and that for the other benchmark, we also significantly execute significantly fewer checks for most of the other benchmark. Something that's worth mentioning here is that basic block, the intra-procedural basic block versioning, so the 100%, actually already remove a lot of type checks. So if we look at the code size now, here we can see that an interesting thing is that for half of the benchmark, we have less code generated. This is due to the fact that these benchmarks are mainly monomorphic. So because we know the type of the variable, we do not have to insert dynamic type checks. So we have less code generated. And on average, we just have 9% more code generated. About the execution time, we have a good result here too. Actually, almost all the benchmarks are faster, and a good news is that no benchmark is really significantly slower. The best result is for the FIB-FP benchmark, which is 2 times faster. If we look at the compilation time, obviously the compilation time increases for most of the benchmark, but most of the time it's only a small increase. But the worst case appear for the paraffins benchmark, which is up to 4 times slower to compile. If we look at the total time, so this time we consider garbage collector time, compilation time, and execution time. Here we can see that we have really a large speed up for the benchmark that uses intensively floating point numbers. This is due to the fact that because we know that the variable are floating point number, we do not have to generate boxing code and tagging code. So yeah, most of the benchmarks are faster here. So just a little conclusion. We did it. We have a lazy and interprocedural specialization in the compiler. We show that it works pretty well. We remove up to all the checks for some benchmarks, and we generate a code that is up to 50% faster. And finally, it's a technique that is pretty simple to implement, and it does not require a complex architecture, no static analysis or the use of an interpreter. Last slide, my future work. Our future work, what we are working on right now is on the propagation of other properties. So we work on the propagation of the value and variable relationships. And what we want to explore is function and return address identity propagation to do aggressive dynamic inlining. And the last thing we would like to explore is register allocation information propagation about the function arguments and the value returned by the function call. That's it. Thank you.
Hello, I'm Phil Pieslow. I manage the JavaScript core team at Apple. Can you tell me what happens to the average execution time with your technique? Because you had information in your charts about the average number of type checks and stuff like this, but then when you went to execution time, I didn't see an average.
Yeah, actually the average is written in the paper, exactly the number, I don't remember it, but it's, I think it's something like 15%. I'm not sure, I don't want to say something wrong, but...
Okay, so it is a speed up in the average.
Yeah,
okay.
Because you can see that in this graph that we have no really slower benchmarks, so it's pretty cool.
Okay.
Hi. So these times are relative to basic block versioning without interprocedural specialization, right?
Yes.
So my question then is sort of about startup time.
Okay.
So it seems like you're sort of bounded by the number of specializations you actually end up needing in practice, but I could write a sort of, nasty program that just uses every possible type and every possible combination. But okay, fine, I could write such a nasty program. My concern is more, well, let's say I wanted to worry about startup time and I wanted to just make a simple baseline JIT. Is it sort of substantially more complicated to just call into one of these functions now that there isn't an unspecialized version staying around? Could it have a baseline JITted version? Is there sort of an incompatibility there, or is it just that wasn't sort of the goal?
Well, actually, the interesting thing in this compiler is that because the technique is really simple, we use no intermediate representation, we use no static analysis, and the fact is that for small benchmark, even if you do code specialization, interprocedural specialization, you still reach pretty good performances. I don't have any specific numbers, but...
Okay, let's thank Baptiste again.